Hello students, welcome to EPG Pathshala. I am Mahavir Singh from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Magnetic Properties of Solids under the paper Solid State Physics. So students, let us see what we are going to learn in this module. To learn the cause of magnetism, how it originates, what are the sources of magnetism. Then we will also learn the types of magnetism, and we will also discuss and learn the classical theory of diamagnetism and quantum theory of diamagnetism. We will also learn the classical theory of paramagnetism as well as quantum theory of paramagnetism. Magnetism has been a human curiosity for nearly 3000 years and evolved as one of the most interesting and fascinating branch of science and technology. We know that electrons have an intrinsic magnetic moment associated with the spin angular momentum and an orbital magnetic moment associated with the orbital angular momentum. So, magnetic moment is linked with both spin and orbital motion of electron. The nucleus also has a small magnetic moment, but it is insignificant compared to that of electron and does not affect the overall magnetic properties. So, there is no contribution from the nucleus. So, we talk only about magnetism coming from the spin motion of electron and the orbital motion of electron. In large number of elements, magnetic moment of electron get cancelled in accordance with the Pauli exclusion principle. So, if we have a large number of elements, so generally magnetic moment, whether it is from spin motion or whether it is from orbital, it cancel. However, in transition metal atoms, the magnetic moment do not get cancelled, therefore are common example of magnetic materials. In transition elements, the spin of the electron is only responsible for the magnetic moment, but in case of rare earth element, however, the effect of orbital motion of electron does not get cancelled, and hence both spin and orbital motion contribute to the magnetic moment.
Diamagnetism. The diamagnetism can be regarded as originating from shielding currents induced by an applied field in the filled electron shells of ions. Classically, diamagnetism is related to changes in the orbital motion of electrons known as Larmor precession that occurs when atomic systems are placed in a magnetic field. Atoms or ions in which the orbital and spin angular momenta cancel in pairs have J equal to 0 and have no permanent magnetic moment. It may be recalled that the current induced in closed electrical circuit by a magnetic field is always in such a direction so as to keep the total flux unchanged. Thus, the circuit has a negative susceptibility. The effect is retained even in system of charges that must be treated by quantum mechanically also as well as quantum mechanically responsible for diamagnetism. In order to discuss the classical theory of diamagnetism, let us consider the Bohr model of the atom in which central nucleus is surrounded by revolving electrons with some frequency, say omega naught, as shown in figure 1. External field is applied, the current changes so as to oppose the change in flux as per the Lentz's law also. This appears as a change in the frequency of revolution. In the absence of external field, the force acting on the electron will be F is equal to m omega naught square r, which is equal to Z E square over 4 pi epsilon naught r square, where epsilon naught is the permittivity of this free space. This is compensated electrostatic force. If we further simplify, we achieve the omega naught equal to Z E square over 4 pi epsilon naught r cube square root, where r is the radius of the orbit, Z E is the charge, and m is the mass of the electron, as shown in figure 1. In presence of magnetic field, the Lorentz force acting on the electron can be F equal to EV cross B, where V is the velocity and B is the magnetic field, and remember this B is perpendicular to R, then F comes out to be ER omega B, where omega is the frequency in the presence of field. Now if we further simplify, this m omega square r equal to Z E square over 4 pi epsilon naught r square minus ER omega B, and omega, if further simplify, this m omega square r equal to m omega naught square r minus ER omega B. Negative sign will Lorentz force represent the negative charge. So now this equation 6 can be further simplify, omega square plus EB over m minus omega naught square, which is equal to 0. On solving this equation 7, we get this omega is equal to minus EB by m plus minus EB square by m plus 4 omega naught square square root over 2, and omega further equal to minus EB by 2m plus minus square root EB square by 2m plus omega square. If EB by 2m is less than omega naught, then omega comes out to be plus minus omega naught minus EB over 2m. Plus minus sign on omega naught means that those electrons whose orbital moments were parallel to field and those whose moments were anti-parallel are speeded up by an amount EB by 2m. This result is called Larmor theorem. This frequency change gives rise to the magnetization. The reason for this is that the frequency change is equivalent to an additional current, and this current component in every atom is in the same direction, whereas the original circulating current were in the random direction and cancel each other. In absence of the field, the electron motion produce no net current or flux. In the presence of field, we can write a current for each electron due to its frequency change. So this additional current is given by this I is equal to minus ZE 1 by 2 pi EB by 2m, which is equal to minus ZE square capital B over 4 pi m. So this magnetic moment of a current loop is given by mu equal to minus ZE square B over 4m into rho square, where rho square is the average radius of the electron from the field axis. If the field is in the z direction, then rho square is equal to x square plus y square, and r square is the average radius from the nucleus, then r square is equal to x square plus y square plus z square. If the atom has spherical symmetry, then x square is equal to y square equal to z square. Therefore, rho square is equal to 2 by 3 r square. This result express the fact that projected area of a great circle with respect to the equatorial plane is less than pi r square. Therefore, this mu comes out to be minus ZE square B by 4m into 2 by 3 r square, which is further equal to minus ZE square B by 4m into r square. If n is the number of atom per unit volume, then this m comes out to be n into mu, and the diamagnetic susceptibility per unit volume comes out to be minus mu naught n into mu by B minus mu naught n ZE square over 6m r square. It is evident that this equation 16, that diamagnetic susceptibility is independent of temperature, and this result is known as classical Langevin result. Quantum theory of diamagnetism. we already know that from classical theory of diamagnetism, that susceptibility which comes out to be negative and independent of temperature, and it comes out to mainly from the induced orbital angular momentum of the electron. Now in quantum mechanical treatment, we have to consider that electron are described by a wave function phi, where phi square at every point is the probability of finding the electron. Alternatively, we may consider the electron as a charge cloud of intensity phi square at each point in space. It can be shown that the quantum mechanical result is correctly given by equation 16, provided we use the expectation value for the squared electron position parameter r. That is, expectation value of r square equal to integration r square mod of phi r square dr over integration mod of phi r square dr, where integration extend over whole space. The Hamiltonian for a mononuclear system under the influence of magnetic field can be expressed as h dash equal to iota E h cross over 2mc into del dot A plus A dot del bracket close plus E square over 2mc square A square. These terms can be considered as small perturbation for an atomic electron. If we consider that a uniform magnetic field is applied in the z direction, then we can write as below: Ax equal to minus half yb, Ay equal to half xb, Az equal to 0. Therefore, the equation 18 can be written as h dash equal to iota E h cross b over 2mc bracket x curly over curly y minus y curly over curly x bracket close plus E square b square over 8mc square bracket x square plus y square bracket close. For spherical symmetric system and by first order perturbation theory, the second term on the right hand side gives a contribution as given: E dash equal to E square b square over 12 mc square r square, expectation value r square. Therefore, the associated magnetic moment is diamagnetic and is given below: mu equal to minus curly E dash over curly b, which comes out to be minus E square capital B over 6mc square into r square. This results in agreement with classical. If we compare the both result, the only difference between classical and quantum is that here we have considered the electron as in the form of wave function, and the conclusion is this susceptibility is negative. This is first, and this susceptibility has nothing to do with the temperature. It is independent of temperature. This is also important that this diamagnetism, which is the universal phenomena, can say that every material is diamagnetic in character.
Paramagnetism occur in those atoms which have permanent magnetic moments. Paramagnetic material have positive magnetic susceptibility. The direction of magnetization is parallel to the applied magnetic field. The permanent magnetic moment of atom result from the following contribution, that is intrinsic or spin moment of the electrons, the orbital motion of the electron, the nuclear magnetic moment. Paramagnetism is found in all atoms having odd number of electrons. The atoms of group first, third, 5th and 7th of the periodic table satisfy this condition. But here I want to mention that if atom forms a diatomic molecule, then it will be out of consideration, as in a diatomic molecule the two electrons have a chance to pair up. atoms with unfilled inner shell, the rare earth element and the transition element have atoms with unfilled inner shell. Then free radicals, some organic compounds have a single unpaired valence electron, so these can made stable under certain circumstances. So all these they are responsible candidate for paramagnetism. For metals, the electrons in metals, some metals also show the paramagnetic character. The electrons in metal behave in many respects as if they are free to move throughout the lattice like molecules in a gas. So they tend to pair up, but there are always few unpaired electrons to produce weak temperature independent paramagnetism known as Pauli's paramagnetism.
The classical theory of paramagnetism. The classical theory of paramagnetism was developed by Paul Langevin. He considered a paramagnetic gas in which each atom or molecule possesses a permanent magnetic moment. He neglected the mutual magnetic interaction between the gas particles. The dipoles tend to align in the direction of magnetic field when an external magnetic field is applied, and this alignment is hampered due to thermal agitation. Thus, equilibrium is established and the dipoles orient themselves with respect to the applied field as shown in figure 2. The probability that a dipole is oriented at an angle theta to the direction of applied magnetic field is proportional to Boltzmann factor exponential minus mu b cos theta over kBt. According to statistical mechanics, the number of molecules dn having inclination theta and theta plus dn and which fall in solid angle 2 pi sin theta d theta is given as dn equal to c exponential minus mu b cos theta by kBt into 2 pi sin theta d theta.
Now, classical theory of paramagnetism was developed by Langevin. He considered paramagnetic gas in which atom or molecule possess a permanent magnetic moment. So the figure shows the orientation, how it can orient. Classically it can have any kind of orientation. Through the classical we calculate the susceptibility of the paramagnetic substance which is independent of temperature, and also classically it is possible that due to thermal motion the spin of the paramagnetic substance are random, and on average net magnetic dipole moment is 0 in the absence of field. But if we apply the magnetic field, then because of the experience of torque of each spin, they tend to align in the direction of field and gave us the net magnetic dipole moment in the presence of field. But again, if we switch off the field, again there is net magnetization again is 0. So one thing is clear, paramagnetism gave us magnetism only in the presence of field. In the absence there is no. That is why the application of paramagnetic materials are negligible.
Therefore, the average component of the magnetic moment of each atom having the direction of the field multiplied by the number of atoms per unit volume n gives magnetization m, given below. M equal to n mu integration from 0 to pi exponential minus mu b cos theta by kBt into cos theta sin theta d theta over integration 0 to pi exponential minus mu b cos theta over kBt sin theta d theta. By solving this equation 24, m comes out to be n mu into cot hyperbolic x minus 1 by x, where x is given as mu b by kbt. This m comes out to be n mu lx, where lx is known as famous Langevin function. This function is very important for theoretical calculation purposes. So if we plot the curve between Langevin function and versus this mu b by kbt as shown in figure 3, it can be seen from the figure that for large value of x, that is for high field strength, basically x, what is x? X is directly linked with magnetic field. So large value of x means magnetic field strength is large, and for low temperature Lx approaches to unity. So that is when x is very smaller than 1, then Lx Langevin function comes out to be x by 3. Therefore m comes out to be n mu square b by 3 kbt, and since susceptibility of para is mu naught b by b, therefore susceptibility of para comes out to be mu naught n mu square 3 kbt, which comes out to be c by t, where c is constant, which is known as Curie constant, which is equal to mu naught n mu square by 3 kb, and this equation 26 is known as famous Curie law. From this law, it very well established that this susceptibility is strongly dependent on the temperature. That is, if we increase the temperature, this susceptibility decreases. Whereas it was not the story with diamagnetism, where susceptibility was negative and it was independent with temperature. Quantum theory of paramagnetism. Before starting the quantum theory of paramagnetism, it is necessary to highlight an interesting difference between the classical and quantum theory. In quantum theory, the permanent magnetic moment of a given atom or ion is restricted to finite set of orientation relative to applied field. That is, orientations are quantized. Whereas in classically there is no such condition. Classically there can be any kind of orientation, but quantum restricts the orientation because of the phenomena of quantization. So orientations are restricted and are quantized. So let us consider a medium having n atoms per unit volume and having the total angular momentum quantum number of each atom as j, magnetic dipole moment mu in free space, and j are related as mu equal to minus g mu bj, where j is equal to L plus S. We know that this j is total angular momentum, L is from orbital and S is from spin, and also quantum mechanically magnitude of j is given as j into j plus 1 over whole square root, and this is the difference also. The quantum mechanically the magnitude of j is j into j plus 1 square root, and there are 2j plus 1 ways. There are 2j plus 1 ways. Orientation is restricted as per the condition of this quantum mechanics, where mu b is the Bohr magneton and g is the Landis g factor. Its value is 2. And the total angular momentum of dipole is due to electron spin, and 1 if it is due to orbital motion only. So by this g comes out to be 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 over 2j into j plus 1. The possible component of magnetic moment along the field direction is given as mu z equal to minus g mj mu b, where mj is the azimuthal quantum number and has values mj equal to j minus 1 dash 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 up to minus j. So the potential energy of magnetic dipole with component g mj mu b along magnetic field b is given as u equal to g mj mu b into b. As per the statistical mechanics, this magnetization can be written as n summation from minus j to plus j, g mj mu b exponential g mj mu b b over k b t over summation from minus j to j exponential g mj mu b into b over k b t, where the coefficient of n, capital N, is the statistical average of magnetic component per atom along the field. Now there are two possibilities. That is case first, when g mj mu b b over k b t is very smaller than 1, that is temperature is very high and applied field is small. Then this exponential g mj mu b b over k b t is equal to 1 plus g mj mu b b over k b t, and this equation 31 becomes m equal to n summation from minus j to j g mj mu b into 1 plus g mj mu b into b by k b t over summation from minus j to j into 1 plus g mj mu b b over k b t, and summation minus j to j over mj is 0, and summation minus j to j mj square is equal to j into j plus 1 into 2j plus 1 over 3, and summation minus j to j 1 equal to 2j plus 1. Therefore this 33 becomes m equal to nbj into j plus 1 g square mu b square over 3 kbt. So this susceptibility of paramagnetic comes out to be mu naught m over b, and which is further, if we put the value of m, mu naught nj j plus 1 g square mu b square by 3 kbt, which comes out to be mu naught n mu j square over 3 kbt, where mu j square is j into j plus 1 g square mu b square. Now let us discuss the case second, when g mj mu b b over kbt is not small as compared with unity, the temperature is low and applied field is stronger. In this case, exponential term cannot be approximated. If we take g mu b b over kbt equal to x, then equation 31 becomes m equal to n summation from minus j to j g mj mu b exponential mjx over summation minus j to j exponential mjx. So this m comes out to be g mu b over d by dx log summation minus j to j exponential mjx, and if we further simplify this, it comes out to be m equal to ngj mu b bj alpha, where alpha is jx. This bj alpha comes out to be 2j plus 1 over 2j cot hyperbolic 2j plus 1 into alpha over 2j minus 1 by 2j cot hyperbolic alpha over 2j, and this bj is known as Brillouin function, and when j approaches to infinity, then Brillouin function is equivalent to Langevin function. So this is also very important. If we compare both statistics, that is classical and quantum, classical theory and quantum theory, in classically it was described by Langevin function, and in quantum mechanically it is described by Brillouin function. So at j approaches to infinity, this Brillouin function is equivalent to Langevin function. So both classical theory as well as quantum theory beautifully describe the cause of paramagnetism theoretically.
So student, let us now summarize what we have learned in this module. Diamagnetism is associated with the tendency of electrical charge partially to shield the interior of a body from an applied magnetic field, and this diamagnetism, which is universal in nature, and this diamagnetism, susceptibility of this diamagnetism is independent of temperature. For high field strength and for low temperature, the Langevin function approaches to unity as for classical Langevin function, and in fact classical theory of paramagnetism suggested a method to calculate susceptibility, but it has major drawbacks too. Since in classical theory the mutual interaction between the gas molecules was neglected, but it's a matter of fact that there is always an interaction between mutual atoms or molecules. So thus, by considering this drawback, it was realized to develop the quantum theory of paramagnetism. So basically quantum theory was developed so as to explain whether it is associated with diamagnetism. There is also quantum theory for diamagnetism, and there is also quantum theory of paramagnetism. But one thing is clear, at somewhere the classical theory and quantum theory, there is correlation as far as this diamagnetism or paramagnetism is concerned. And we also conclude in this that diamagnetism, the susceptibility of diamagnetism is negative, it is independent of temperature, whereas susceptibility of paramagnetism strongly depend upon the temperature. So thank you.